In this video, I'm going to be talking about scattering and tunneling in Bohmian mechanics. And so recall that pilot wave theory says it can be, or that it can recapitulate all the predictions of textbook quantum theory using just the Schrodinger equation for the evolution of the wave function, which is this. This is the time-dependent Schrodinger equation, and the guiding equation for the particle's velocity in response to the wave function. So this is the guiding equation, which tells us the velocity of the particle, and the velocity of it is going to be based on what the wave function is in the region around where the particle is. And so in the two papers, so the first one is the pilot wave perspective on quantum scattering and tunneling, which is what this video is going to be based on. And the next video is going to be based on this one, so the pilot wave perspective on spin. So these are both 2013 papers by Travis Norson, whose book I am using as a guide to these videos on the foundations of quantum mechanics. And so these two papers attempts to show how pilot wave theory gives the same predictions for scattering and tunneling, which is the first paper that I'm going to talk about in this video, and for spin and entanglement, which is in the second paper that I'll talk about in the next video. So it's trying to show how pilot wave theory can give the same predictions as textbook quantum theory. And so as I said in a previous video, these are necessary but not sufficient conditions for a candidate interpretation of quantum mechanics to be plausible. By that I mean any interpretation of quantum mechanics has to at least be able to explain the predictions that we get from textbook quantum mechanics, because the predictions that we get from textbook quantum mechanics is so successful that if you come up with an interpretation of quantum mechanics and it can't explain those predictions, or even worse, if it gives the wrong predictions, then your candidate, well, is not going to be a candidate for a interpretation of quantum mechanics. And so what this means, though, is that neither of these papers offers any new or deep insight into reality, but simply demonstrates how pilot wave theory gives the same predictions for the phenomena as textbook quantum theory. And so, as I said, this video is going to cover this paper here, so the pilot wave perspective on quantum scattering and tunneling. And so if we think about textbook scattering, what we get is this. So we have these waves here. So this one shows this A with the arrow pointing right as the incident wave. It comes at this potential here. So this is a step potential where when x is less than 0, then it's 0. And when it's greater than 0, then it's equal to some value v naught. And so this wave comes here and it can do one of two things. It can either reflect and go back towards the left, or it can transmit and go to the right. This I got from Wikipedia, and it shows that there is a zero wave, I guess, coming in from the left here, so a zero incident wave from the left. In textbook quantum theory, all we have is that wave, right? And so it's just telling us probabilities of where we would find the particle if we did a measurement, say over here on the right side, so in this potential, or on the left side, on this side of the potential here. So we could come up with probabilities for it transmitting or for it reflecting off of this potential. And that, like I said, is textbook quantum mechanics, and it gives good predictions. And so we have to have that Bohmian mechanics can also give those same good predictions. And so this is textbook quantum tunneling, where we have our wave coming in. We have this potential here, which only goes from some x to some a. Usually that's how it's written, where it doesn't keep going to the right the way it does when we're talking about the scattering here. So we just have kind of this block of potential here. And so we see that the wave function can tunnel through this. So it can, then we get this small wave function on the other side right here. And so again, our Bohmian mechanics is going to have to at least give the same prediction that textbook quantum tunneling does. And so this is just a GIF here of quantum tunneling, where we see the incident wave coming in from the left. It hits a potential right here at x equals 0, and then we get some reflection and some transmission right here. All right, so what is written down below here is in these lecture notes is copied almost verbatim from the Norson 2013 paper. But of course, by no means it's the entirety of the paper. I'm not going to go through the entire paper, but there are some minor alterations, exclusions, and additions that I added in here for clarity. If you want to read the entire paper, obviously that's going to be linked to in these lecture notes, which are linked to in the description down below. So you can check out the paper in its entirety if you so desire. So for quantum scattering, what we want to do is look at a wave packet of length L that scatters off a step potential. So again, we're looking at this step potential where the potential is 0 when x is negative, and it's greater than 0 when x is positive. And so this will give us these as our wave functions. So when x is less than 0, so when x is negative, we have this with the A, which is our incident wave, then this one with B, which is our reflected wave, then this one with C, which is our transmitted wave. And the other thing to notice is that when we are to the left of the potential here, we have these K sub naughts. So these are the wave numbers here in our exponents, where when we are in the transmitted wave, it's a kappa sub naught, where the K is equal to 2me, E being the energy of our particle over h bar squared. Then the kappa has this E minus the potential right here. So it's lower in energy. We can see that this is going to be a smaller number than the K right here. So like I said, we have A is the amplitude of the incident wave, B the amplitude of the reflected wave, and C the amplitude of the transmitted wave. And so since the leading and trailing edges of the reflected packet are produced respectively when the leading and trailing edges of the incident packet arrive at the barrier, and what that means is that we have this incident wave right here. When the leading edge of this hits this barrier here, it hits this potential, it will produce the leading edge of both our transmitted and our reflected waves here. And when the trailing edge of our incident packet here hits the potential, then that will produce the trailing edge of both our reflected and our transmitted waves here. And since the reflected packet propagates in the same region as the incident packet, so their group velocities are the same, the reflected packet has the same length L as the incident packet. So this gives us the probability for reflection being equal to this. And so we will be using this in the future in this video. And so where the last step we used that the ratio of the amplitude of B over A is equal to the K sub naught minus kappa sub naught over K sub naught plus kappa sub naught. And so that relates the amplitude B of the reflected packet to the amplitude A of the incident one. And we can see up here in this figure, the way they show this, the amplitude of the incident packet is larger than the amplitude of the reflected packet there. And that what we can see in the fact that we have a negative here for our B amplitude and a positive here for our A amplitude. So the result here is in agreement with the equation. So this is an equation from earlier in the paper and a part that I haven't copied here, so that's why I put it in red, but this is just in agreement with the probability for reflection here in textbook quantum mechanics. So the transmission probability can be calculated in a similar way, but it is crucial to recognize that the group velocity for x greater than 0, so that's the transmitted wave here, so the group velocity for that in that region is smaller than the group velocity for the incident and reflected waves here. Thus, the position of the leading edge of the transmitted packet when the trailing edge is created at x equals 0, i.e. the length of the transmitted packet, is only this. And so this is telling us that the length of the wave packet here for our transmitted wave is smaller by this factor of kappa over k here. Remember that kappa is smaller than k. And so this is going to reduce the length of our transmitted wave here. And we can see that in this figure here, where this is L, the incident wave is a length L, the reflected wave is also the length L, but the length of the transmitted wave is something shorter than those two. So that is, the transmitted packet is shorter by a factor of kappa over k than the incident and reflected packets. The total probability carried by the transmitted packet is then seen to be this. So this is the probability of transmission here, which is going to be equal to this right here. So again, in agreement with the earlier result for the textbook quantum theory. Note, though, on this analysis how this perhaps puzzling factor of kappa over k in this, so this was the earlier result that he is talking about here. And so this admits an intuitively clear origin in the relative lengths of the incident and transmitted packets. So in the pilot wave theory, the particle velocity is determined by the structure of the wave function in the vicinity of the particle. So remember, that's what our guiding equation is telling us, is the velocity of the particle being based on sort of the local structure of the wave function where the particle is actually located. And so we get the velocity using this, where J is our probability current, and then the rho here in the denominator is our probability density, and we are evaluating this at the position of the particle. So that's what I meant by the structure of the wave function in the position of the particle. So by considering a plane wave packet, so again, we're approximating the plane wave by having this L be very long, where the trailing edge and the leading edge, which are the non-plane wave regions of it, are much, much smaller than our L here. So by considering a plane wave packet, that's what he means by a plane wave packet, we can see that there are several possible regions in which the particle may find itself. So let us consider these in turn. And so what we're talking about is we have this plane wave packet here, and then the particle, which I just arbitrarily drew here, could find itself in any region within this. And the reason we want our L to be much longer than the trailing and leading edge is that we want the probability of finding the particle in the plane wave part of this packet to be much, much higher than the probability of finding it in one of these edges here, where the math would get a bit more complicated. So to begin with, initially the particle will be at some random location in the incident packet, since by assumption the packet length L is very large compared to the length scale associated with the packet's leading and trailing edges, which is what I was talking about up here. The particle is overwhelmingly likely to be at a location where the wave function in its immediate vicinity is given by this, where this is a plane wave function right here. Here, and subsequently, we omit for simplicity the time-dependent phase of the wave function, which plays no role. And so we're just going to be focusing on the plane wave here, not the sort of time evolution of the phase for it. It follows immediately that the particle's velocity is this. So again, this is the probability current for our incident wave and the probability density of our incident wave. And so that gives us this, where this a squared and this a squared will cancel out. So we end up just getting this right here for our velocity of the incident wave. Note that this is the same as the group velocity of the incident packet. Thus, the particle will approach the barrier with the incident packet, but keeping its same position relative to the front and rear of the packet as both things, the wave and particle, move. So he's saying that the particle, if it did happen to be found here, would not like move over here or over here or over here, some other place within this wave. It will maintain its position inside the wave. At some point, the exact time and place, depending on its random initial position within the incident packet, so that's the quantum equilibrium hypothesis there, the particle will encounter the leading edge of the reflected packet. It will then begin to move through the overlap region where both the incident and reflected waves are present. So this right here is telling us the overlap region. This the O on here is. So its velocity in the overlap region will be given by this right here, where we see we have this factor here that has this phi in it, and this is the complex phase of B relative to A. And so in this case, it is 0 for this scattering. We'll see when we get to the tunneling that we cannot just think of that as 0. So the particle's velocity will oscillate around an average drift value given by this. So this is the velocity in the overlap region. And since we're assuming that the packet length here is much greater than the wavelength, which is equal to this 2 pi over k naught, the particle's velocity will, with overwhelming probability, oscillate above and below this average value many times. So we get this oscillation because of this cosine here. So it's oscillating around some value, and it's doing that really fast. And so as it moves through this overlap region. So it is thus an excellent approximation to simply ignore the oscillations and treat the particle as moving through the overlap region with a constant velocity rather than a velocity that's sort of oscillating around a particular velocity. So there are two possible ways for the particle to escape from the overlap region. If it arrives at the origin, it will cross over into the region where only the transmitted wave is present. It will then continue to move through the right with a velocity here. So this is our transmitted velocity, matching the group velocity of the transmitted packet. The other possibility is that while still in the overlap region, the trailing edge of the incident packet catches and surpasses the particle. It will then subsequently be guided exclusively by the reflected wave, which is this right here, and this will be its velocity right here. So we have the k naught here rather than the kappa naught here, which will match that of the reflected wave packet with which it will propagate back to the left. So it's helpful to visualize the family of possible particle trajectories on a space-time diagram. So he refers us to figure 2 here. And so this is what we are looking at, where this is a space-time diagram. So the x-axis is space, the t-axis, this vertical t-axis is our time. And so we see our wave packet, which has this length right here, is moving towards this potential at x equals 0. And so we see that at different times, it's getting closer and closer to it. So at different time slices, different horizontal time slices, it gets closer and closer to it. And then here at the origin, we actually have this run into our potential. And so that's when we start doing this reflection and transmission here, where we see this dotted line here is transmitted, where this dotted line is being reflected and it's moving through our incident wave here. And so in this triangular region right here, this is our overlap region. And we see that the wave or the particle velocity actually slows down within this region here. And that's because we have the velocity here, which is slowed down when compared to our incident particle velocity. So if we just count this as being 0, we get this as our velocity, and so it's slowed down within this triangular region right here. And then we get the trailing edge of our wave packet, so that's marked by this dotted line here. It comes up here and then hits right here, and then it can either be transmitted or it can be reflected here. And each of these solid lines inside here are possible world lines that a particle within this wave packet could take. So we see that some of them are going to be transmitted while others are reflected here. And so we see that this has to do with whether these slowed down particles in the overlap region run into the potential first or run into the trailing edge of our incident wave first. And so if they hit the potential first, they transmit. If it hits the trailing edge of our incident wave, then they will reflect. And so this has to do with where inside the wave packet that the particle was located. So remember up here, I put the particle here, but it could have been based on the quantum equilibrium hypothesis, sort of anywhere on here. But if it's in the front part of this wave packet, then it will transmit. And if it's in the back part of it, then it will reflect, because we see here that if it's in the front part, then when we end up running into the potential here, the particles on these world lines are going to hit the potential before they hit the trailing edge of our wave packet here, and so they will transmit. But if they were in the back part of our wave packet here, then after slowing down, they will hit the trailing edge of our wave packet here and be reflected. And so I'll read through here. So again, it's helpful to visualize. He says, notice that a particle which happens to begin near the leading edge of the incident packet will definitely transmit, while particles beginning near the trailing edge of the incident packet will definitely reflect. Although the dynamics here is completely deterministic, the theory makes statistical predictions because of the initial position of a particular particle within its guiding wave is uncontrollable and unpredictable. So again, the thing he's trying to establish here is that we can get these statistical predictions that we get from textbook quantum theory, that we can recapitulate those statistical predictions in Bohmian mechanics. And that's what he is trying to establish here. And by using this, he is saying that we have established that we can get these same predictions in Bohmian mechanics that we do from the very successful textbook quantum mechanics. So recall the quantum equilibrium hypothesis, according to which for an ensemble of identically prepared systems with initial wave function here, the initial particle positions will be random with a distribution given by the Born rule here. And then follows from the equivariance property described in the introduction of this paper, and I described it in an earlier video, that our rho here, which is our probability distribution, is just equal to the square of our wave function. We'll continue to describe the particle's probability distribution for all future times t. So the pilot wave theory thus reproduces the exact statistical predictions of ordinary quantum mechanics without any further axioms about measurement. Whereas in ordinary quantum mechanics, for example, the transmission probability equal to the integral of the density here across the transmitted packet represents only the probability that the particle will appear there if a measurement is made. In the pilot wave theory, however, this transmission probability instead represents the probability that the particle really is there in the transmitted packet, ready to trigger a click in a detector should such a device happen to be present. And so a concrete illustration of the equivariance property that guarantees the equivalence between the pilot wave theory's statistical predictions and those of ordinary quantum theory let us derive the reflection and transmission probabilities directly from the particle trajectories. And so the key here is to examine what he calls the critical trajectory. So if we zoom in on this figure up here, so we want to zoom in on this overlap region here, we see that, like I was saying, if the particle is in this part of the wave function, it will hit the potential before the trailing edge of the incident wave, and so it will transmit. Whereas if it is in this part, then it will hit this trailing edge of the incident wave first, and then reflect. And so we have this critical trajectory, which is right in between there. So a zoomed in image, like I said, is right here. As explained in the caption, the critical trajectory moves through the overlap region across a distance, which I'm calling XL here. He didn't actually use that in the paper, but I'm calling it X sub L, and I put that sub L there just to tell us that it's going to be dependent on this L here in this part of the equation. So he just gives this in the paper, but I'm calling it X sub L here. Where this probability here is the transmission probability. So it does this in a time t minus tau. So that's what he's talking about right here. So this is our t minus tau right here. And so it transmits if it does this in a time t minus tau, where t is equal to the length of the wave packet here divided by h bar, and then k sub naught, which is the wave number for our wave packet there. And tau is equal to this right here. It follows that the average velocity through the overlap region, which I put this in here, so we want to look at the velocity in the overlap region, is this distance divided by this time right here. And so that's how he gets this, which I put here in brown is our final result from taking this right here and dividing it by this minus this. So equating this with the expression for the velocity in the overlap region that we worked out earlier, which remember was this right here. We equate those two because those are both for the overlap region velocity. We can solve for the probability of transmission to get this, once again, using this relation right here. To put this in terms of the wave numbers k sub naught and kappa sub naught, this gives back precisely this, which is our probability for transmission. And so since we have that our PR, so the probability for reflection is just 1 minus the probability for transmission, because we have to have our probabilities add up to 1. The equation from earlier, which remember this was our equation for the probability of reflection, is also implied again by the properties of the critical trajectory. So again, it's just saying that anything that's, so if we have our wave packet, if we're looking at it right at this time slice, just the instantaneous time where the leading edge is hitting our potential right here, if the particle is in this part of the wave packet, then it will be transmitted, and if it's to the left of this critical line here, then it will be reflected, because a trajectory will go up here. When it hits this leading edge of the reflected wave packet, it slows down because we get in this overlap region here, and so it bends this way so that we see now we have less of a spatial component to this vector and more of a time component, telling us that it's slowed down. And so anything to the left of that is going to hit this trailing edge of the incident wave packet right here and go into the reflected wave, or anything to the right of it will hit the potential first and be transmitted. So he says, it is of course no surprise that we arrive at the same expressions for the transmission and reflection probabilities by considering the pilot wave expression for the particle velocity in especially the crucial overlap region, which again is this sort of triangular region right here. But it is a clarifying confirmation of the sense in which the wave and particle evolutions are consistent as expressed in the equivariance property. And then, so this is something that I have just added here. So the take-home message for this stuff on scattering. So the wave can reflect or transmit through the potential. So we're just saying that the wave transmits and reflects off that potential. So during the reflection, there is interference in the incident and reflected wave. That's what we call the overlap region there. This interference causes the particle to slow down. So that's why we get this change in velocity here in that overlap region. If the slowed particle meets the trailing edge or the trailing end of the incident wave, then it is reflected. If the slowed particle meets the potential before the incident wave, then it is transmitted. The path in between is the critical path, such that anything to one side reflects and anything to the other side transmits. So this, along with the quantum equilibrium hypothesis and equivariance principle, which just tells us that we don't know where inside the incident wave the particle is, explains how we can get probabilistic results from Bohmian mechanics in quantum scattering. All right, and so the next thing I will talk about is quantum tunneling, which has a lot of similarities, but there is some important differences here. So now, again, we have this step function, but now the potential is 0 instead of just any x greater than 0. So any positive x is between 0 and some A here. So it stops. It doesn't just keep going off into infinity. So then we get this as our wave function. So again, we have this for our incident wave, and then this you could think of as the transmitted wave. So that's the wave that has tunneled. So that's after it has left the potential here into A. Then we have this, which is what is called the non-classical zone, or the classically forbidden region. So again, A is the amplitude of the incident wave, B the amplitude of the reflected wave, C and D the amplitude of the wave in the classically forbidden region, and F the amplitude of the wave that has tunneled through the barrier. So imposing the usual continuity conditions on psi in its first derivative. So that's just telling us that when we are interacting with that potential, that we have to have that it's continuous, that there isn't a discontinuity in our wave. This gives us 4 algebraic conditions for the amplitudes. So if we just ignore C and D, so the classically forbidden region for now, the amplitudes of the reflected and transmitted packets can be written in terms of the amplitude of the incident packet right here, and of the transmitted packet here, or the tunneled packet, I guess you could say. And you'll see that this has these hyperbolic trig functions here, and we'll see in a little bit why that ends up showing up here. So since the packet that develops on the downstream side of the barrier moves with the same group velocity as the incident packet, the transmitted packet length matches the incident packet length. So unlike with our transmission in the scattering, the transmitted packet length will actually be the same as the incident packet length. So we have the probability with the transmitted packet, so the tunneling probability is this, and then we have the probability for reflected here. So again, we see we have these hyperbolic trig functions here, which will be explained in a little bit. So as before, these results can be understood in terms of the particle trajectories as well. In general, the trajectories are very similar to those from the scattering example. While the incident and reflected packets are both present to the left of the barrier, an overlap region is set up in which the motion of the incoming particle is slowed. So just like with the scattering, we get this for our overlap region, where we again have this right here. But as I warned earlier, we now can't just ignore this and call it 0, because remember, with the scattering, it was sort of oscillating up and down, above and below a particular velocity, and so we just kind of took the average of that and called it 0. So we now have a non-trivial complex phase between the amplitudes of B and A, so it's actually going to be equal to this right here. So the average drift velocity through the overlap region, however, remains as in equation 24. So the analysis surrounding figure 3 still applies, and we have again that the transmission, or here tunneling probability, is determined by the critical trajectory. So again, this is just like with the scattering. So in agreement with the results arrive by considering just the waves. This again confirms the distribution of possible particle trajectories evolves in concert with the intensity rho, such that equation 6, which is from earlier in the paper, a part that I didn't show, but it's just this, which is the equivariance property, remains true at all times. So the nature of the pilot wave theory particle trajectories in the classically forbidden region is of some interest. The wave function in the classically forbidden region is this. So this we saw earlier, where the 4 algebraic conditions mentioned just prior to equation 34 imply this, that our d over c is equal to this, where the relative phase theta is given by this. So it's based on the k sub naught over kappa sub naught there. So the fact that the relative complex phase D and C is not 0 is crucial. If this were 0, the probability current J, and hence the particle velocity, would vanish, and it would be impossible for the particle to tunnel across the barrier. Instead, though, we have that this is the probability current right here in the classically forbidden region is equal to this. And so we have this then, the probability density in the classically forbidden region divided by this C here is equal to this big long looking things. And so the particle velocity is then given by this. So now we're seeing that this hyperbolic trig function is showing up here. So thus particles speed up as they cross over the classically forbidden region. And we can see that in this figure here. And so that's where this hyperbolic function comes in, is that when we're in this gray here, which is our classically forbidden region, that's when we're inside of the potential, we see we have these hyperbolic bends on our lines here, so the paths that the particle could take. So they are speeding up while they are inside this potential right here. So the overall pattern is similar to the case of scattering from the step potential. Particles that begin near the trailing edge of the incident packet will be swept up by the reflected packet before reaching x equals 0, while those which begin near the leading edge of the incident packet will reach the barrier, tunnel across it, and emerge with the transmitted packet. And so, yeah, that is the tunneling here for our Bohmian mechanics. And so this for figure 4 says, so again, this is a space-time diagram showing a representative sample of possible particle trajectories. So particles beginning near the leading edge of the incident packet, so that's up here, will tunnel through the barrier and emerge on the far side. So that's the transmitted here. The unusual accelerating character of the trajectories in the gray shaded area, so the classically forbidden region, indeed the mere presence of trajectories here reflects the highly non-classical nature of the law of motion for the particle. Note that the analysis in the main text assumes that the incident packet length L is very large compared to the barrier length A, so the wave packet here is much larger than the potential width right here. This separation of the length scales is not accurately depicted in the figure. So what they're saying is that this looks a lot closer in length to this than what it actually would be. So this wave packet should actually be much, much larger than what we see here, but this is just shown sort of for simplicity. But anyway, that, like I said, is the tunneling, which in a lot of ways is similar to the scattering. But we get these hyperbolic velocities while we are moving through the classically forbidden region. And that is reflected in these hyperbolic trig functions here. But anyway, again, the thing that Norson is trying to show in this paper here and in the next paper that I'll talk about in the next video is that we can recapitulate, we can re-obtain the probabilistic predictions of textbook quantum theory, but we can think about it in a very sort of classical way. You know, it's very sort of intuitive to think, well, if the particle is in the front part of this, then it's going to tunnel through here, and if it's in the back part, then it's going to reflect. That's, you know, a very classical way of thinking about it. Obviously, this is non-classical in that we can even have tunneling here, which is non-classical, but we can reobtain, like I said, the statistical predictions by just thinking about things that are going to tunnel or transmit are in the front of the wave, while things that are going to reflect are in the back of the wave, rather than, you know, some mysterious probability wave that sort of magically collapses into a particle based on this weird thing that we call a measurement. But anyway, I hope you found this video helpful or at least interesting. And I've been saying this in the last several videos. You know, making these videos can be time consuming, and I do have a day job. So if you wanted to throw me a few dollars, I do have a Patreon campaign that you can check out. But anyway, I hope you found this video interesting, and I will see you in the next one.